Let me ask you a question. What is the weight of the universe if scientists can calculate the weight of the Earth, which is about 6 to the 24th power kilograms, and the total weight of the solar system is about 2 to the 30th power kilograms as of 2025, based on estimates from the Hubble telescope and Gaia probe data. The weight of the Milky Way is about 1.5 trillion times the weight of the Sun, since we can measure the weight of these celestial bodies step by step. Then, we also calculate the weight of the entire universe. In the next 30 minutes, let us see how scientists weigh the universe. I also hope this video can wash away the fatigue of your busy day. Watch quietly. Listen quietly, and I wish you a good dream. When it comes to weighing the universe, it is not always as tranquil as the starry sky. When we truly began to weigh the universe, it directly led us to a chilling truth. Theoretically, you should not exist. That includes me and our Earth. In fact, even the universe itself should not exist. All of this began with that nearly impossible moment. A probability of occurrence of just 1 in 10 to the power of 10 to the power of 123 moments. This number is sometimes called the Penrose number, named after Nobel laureate Roger Penrose. It measures the astonishing order and precision that our universe possessed at the moment of its birth. We all know that order and precision decay over time. Like the crumbling walls of an ancient city, the magnificent structures carved by our ancestors thousands of years ago are eventually worn down by time, reduced at last to rubble and dust. Penrose believed the universe should follow the same law. Its inner order and precision would inevitably decay. Just like ancient Egypt, just like those ancient cities in China and Central America. His view: black holes are the ruins of the universe, the final destination of all things, where all order and precision will ultimately give way to an endless abyss. In our universe, there are about 10 to the 80th power protons, neutrons, and other similar particles. They still wander outside the abyss of black holes to this day, maintaining their own order and precision. This makes our universe truly remarkable, like an artifact that never decays. As Penrose repeatedly calculated these numbers, he became convinced that the universe must have been born with an astonishing degree of precision. Its initial entropy was unimaginably low, and probability is exactly that astronomical number, 1 in 10 to the power of 10 to the power of 123. Yet, this extremely large number is not the only mystery of the universe. Take antimatter. For example, it is essentially the mirror image of matter. Whenever the two meet, they annihilate each other, even though there are 10 to the power of 80 protons in the universe. Particles like neutrons exist in abundance, but there are very few antiparticles. This is both fortunate and strange. At the moment of the Big Bang, equal amounts of matter and antimatter had been produced. They would have almost instantly annihilated each other, leaving no trace behind. Yet, in our current model of the universe, there is no theory that can fully explain why the universe has such a strong preference for matter. In fact, based on experimental results, at the birth of the universe, the amounts of both should have been equal. Everything should have been annihilated. You and I should not exist. This universe should not exist at all. And yet, here the universe is. You and I are both here. But there is another prediction, more troubling than the absence of antimatter or the astonishing order at the birth of the universe, that worries physicists even more. And that is the weight of the universe. When theoretical physicists try to unify quantum mechanics and general relativity, they find that the universe should have been crushed by its own weight the instant it was born, collapsed into nothingness. This overwhelming weight does not mainly come from the planets and stars in galaxies, but from the empty vacuum itself. Our universe would normally be crushed by the weight of nothingness. This mystery, this is the famous cosmological constant problem. It is like a ghost that has haunted physicists for nearly a century, and our modern exploration of this problem begins with a brand new understanding of a fundamental concept: energy. In the mid-19th century, a German physician named Julius von Mayer, by studying the relationship between human metabolism and environmental temperature, he was the first to clearly point out whether it is heat generated by the body burning food or heat absorbed from the sun. They are essentially equivalent. He realized a crucial truth: heat is just another form of energy. What exactly is energy? How is this related to the weight of the universe, or the cosmological constant, for that matter? Simply put, energy is the most valuable resource in the world. We use it to power vehicles, to heat our homes. Even the phone you are using to watch this video needs it. As von Meyer realized, energy exists in many forms. As early as the 10th century, humans understood that the essence of energy is the work that drives the world. Whether it is harnessing the drop of water flow or the chemical energy from burning coal, the essence of the Industrial Revolution was to transform one form of energy into another form that could power machines. But Einstein, we see a deeper truth. Mass itself is the ultimate form of energy. To understand this, just remember one iron law of the universe. Nothing can travel faster than the speed of light. Imagine this. If we keep accelerating Usain Bolt, pushing him closer to the speed of light to accelerate, he must constantly take in energy, such as food. But as he gets faster and faster, a strange phenomenon occurs. He finds that trying to speed up, even just a little, becomes incredibly difficult. What is stopping him? Where does the energy he consumes go? Einstein realized that this energy did not disappear, but was instead transformed into his inertia, which is the resistance to acceleration. The faster he goes, the greater the inertia, until, at the threshold of the speed of light, his inertia approaches infinity. No amount of energy could push him past that limit. This thought experiment reveals a startling secret. Energy can be transformed into inertia when Bolt is standing still. What is his inherent inertia? It is his mass. Therefore, mass and energy are essentially the same thing. Einstein captured this idea perfectly with his famous equation. SCI. It encapsulates the concept flawlessly. It tells us that even the tiniest amount of mass m, multiplied by the square of the enormous speed of light c, unleash a truly staggering amount of energy E. Whether it is the explosion of a nuclear weapon or the light and heat at the core of the sun, their power all comes from this transformation of a tiny bit of mass into an immense amount of energy, and this will completely change the way we measure the universe. Because in Einstein's universe, gravity is attracted not just by mass, but by all forms of energy. Light has no mass, but it has energy, so it too is bent by gravity as it passes the sun. So when we ask how heavy the universe is, what we really want to ask is how much energy it contains. This includes the most mysterious part, the energy of the dark universe. So now, it is time to weigh the universe. To answer this question, we first need to define how big the universe we want to measure actually is. More than 2,000 years ago, Archimedes of ancient Greece tried to estimate the size of the universe. He did not believe the universe was infinite. In a book called The Sand Reckoner, he calculated how many grains of sand the universe could hold and came up with a finite number, 10 to the 63rd power. Although his methods and estimate of the universe's size seem wildly inaccurate by today's standards, his core idea was correct. We can use known physics and mathematics to estimate this seemingly infinite universe. How big is the universe we are measuring today? How large is it? We are referring to the observable universe. The universe was born 13.8 billion years ago, which means the light from the most distant places has traveled for at most 13.8 billion years. But things are not that simple, because the universe itself is expanding. It is like you are running backward on a conveyor belt that is constantly getting longer. Even if you run 10 meters, the distance between you and the starting point might be much more than 10 meters. Taking the expansion of space into account, the farthest distance from which we can receive signals today actually comes from 46.5 billion light-years away. Our observable universe is essentially a huge sphere centered on us, with a diameter of about 93 billion light-years. What is beyond this range? We do not know, and we can never know. The laws of physics out there might be completely different. If we want to seriously weigh the universe, what we can do, and the only thing we can do, that is, measuring the observable universe with a diameter of 93 billion light-years. All right? Let us start weighing. The most straightforward way is to count the stars. We know that the mass of one sun is about 2 followed by 30 zeros kilograms, and in the universe there are at least 200 sextillion stars like this. By calculating layer by layer like this, we can get a preliminary estimate The total mass of all luminous matter in the universe is about 2 followed by 52 zeros kilograms. But this method is too rough. It misses a lot of things. Scientists have come up with a smarter way. Instead of counting, they look at the shape of the universe. Imagine that the universe is a giant. The invisible trampoline. How do we know how much weight is placed on it? The answer lies in an ancient beam of light. It is called the cosmic microwave background, or SEAM. This light is the afterglow of the Big Bang. It is like a scout, carrying records of every dip in space and time it has passed through. Precisely analyzing this light, scientists have come up with a more accurate result. All the matter we can see in our universe, stars, planets, nebulae, including you and me, if you add up all their total mass, it comes to about 1.5 followed by 53 zeros kilograms. This number is several times heavier than the result we got from just counting stars. But what comes next is the truly astonishing part. This unimaginably huge number, the sum of everything we can see, actually makes up only % of the universe's total energy or mass. Yes, you heard that right, just 5%. The remaining 95% of the universe is completely invisible. First, there is dark matter, which accounts for 25%. It is like a ghost. It has mass and creates gravity that holds galaxies tightly together, but it does not emit light or reflect light. Light can pass through it, and so can you. Its existence is something we have inferred through its gravitational effects. But even dark matter is not the boss of the universe. The real ruler is dark energy, which makes up as much as 70%. If gravity is the force that holds the universe together, then dark energy is the mysterious force that pushes it apart. We have discovered that distant galaxies are accelerating away from us. It is as if someone is stepping hard on the accelerator of the universe. Accelerator is dark energy. It is a form of energy that fills all of space and has a repulsive force. The final inventory and weight of our universe looks like this. 5% ordinary matter, 1.510 circumflex 53 kilograms, 25% dark matter, about 5 times the amount of ordinary matter, 70% dark energy, which is more than twice the combined amount of ordinary and dark matter. Add all three together. We finally obtained the true total weight of the universe. And this weight has finally led us to the core mystery we face today. What exactly is this dark energy? All the data points to a peculiar substance, whose energy density is almost constant throughout the universe. As we will soon understand, this is precisely the characteristic one would expect from the energy of a vacuum. It turns out that a vacuum is not empty. In fact, it is a bubbling soup made up of virtual particles, constantly and endlessly boiling. These particles continually pop in and out of existence. They give the universe its weight. They give it energy. The energy of the vacuum goes by many names. The early days of quantum mechanics, people mostly called it zero-point energy. People now often refer to it as vacuum energy, or the cosmological constant. They both point to the same thing, which is also what most scientists believe to be the essence of dark energy. The dark energy contained in our observable universe is roughly equivalent to the energy of 460 trillion tons of tent. When you add up all the matter and energy, you will find that the total energy contained in the universe is equivalent to 67 quadrillion tons of tent explosives. That is the weight of the universe. It sounds like a lot, but do not forget, all that energy is spread evenly throughout a vast universe. With an extremely low density, dark energy is so thin that the amount of dark energy in a coffee cup-sized space is not even enough to crush the smallest bee in the world. This is actually fortunate. It is precisely this low density that has allowed the universe to grow both old and vast. However, in the process of weighing the universe, we have run into one of the biggest mysteries in cosmology, the cosmological constant problem. If you really believe that dark energy is the energy of the vacuum, then why is its amount so small? Because, when we take those time-tested theories of physics seriously, we find that the zero-point energy should be enormous. Our universe should not be this gently evolving cosmos we see today. It should have been born a heavyweight champion. The instant it came into existence, it should have been crushed by its own vacuum energy, warped into nothingness by the fabric of space-time, and torn apart by gravitational tides. It vanished in the blink of an eye. Our universe was never supposed to have the chance to become old and vast. It was never supposed to allow intelligent life to evolve. It was never supposed to let you exist, but the universe did become old and vast. It did allow you to exist. In fact, the universe is not a heavyweight at all. It is not even at flyweight level. So here's the question. Why is dark energy so little? Where did all the zero-point energy go? Why has not it destroyed the universe? Back in 1920s Germany, physicists were already fiercely debating zero-point energy. That is, the energy of the vacuum itself, does it really exist? One side, represented by physicist Otto Stern, believes that zero-point energy truly exists. His calculations show that only by considering the effects of zero-point energy can certain phenomena observed in experiments be explained. On the other side, represented by the famous Wolfgang Pauli, he raised a fatal counterargument. Pauli pointed out that if zero-point energy really existed, and possessed as much energy as the theory suggested, then its gravitational effects would be catastrophic. Pauli did a rough calculation on the spot. He came to a startling conclusion. Under such enormous vacuum energy, the universe would be crushed by its own weight. Its scale can't even reach the moon. This is the nature of the cosmological constant problem. On one side is the enormous vacuum energy predicted by quantum mechanics. On the other side are the catastrophic gravitational consequences predicted by general relativity. Between the two, there is a huge gap. Where does this mysterious vacuum energy actually come from? Imagine the universe around you. It is filled with stars, menacing red giants to sickly glowing white dwarfs. Their light illuminates the entire universe. Various uninhabitable planets orbit around these stars. Of course, there are also warm and pleasant planets like Earth, and towering clouds of gas. The spectacular, colorful wonders of nebulae, that is where stars are born. All of these things carry mass, carry energy. Imagine a cosmic law enforcer enters the universe and takes all of this away. Everything, dead or alive, big or small. What would be left? The answer is, nothing would be left. A dark, silent, truly desolate place, the purest emptiness. Intuitively, you might think this void is weightless. After being completely emptied, it should contain no energy at all, but that is not the case. At least, we do not think so. Quantum theory tells us, vacuum itself carries energy. It carries zero-point energy, that is, vacuum energy, also known as the cosmological constant. As early as 1911, the famous German physicist, the father of quantum mechanics, Monty Planck, had already contemplated the idea of zero-point energy. Not long after, another German, Walther Nernst, proposed that the vacuum is not empty, but rather a strange medium filled with immense energy. However, the relationship between Einstein and zero-point energy, as well as the independent concept of the cosmological constant, was quite complicated. At first, he supported both ideas. In 1917, he proposed the concept of the cosmological constant, believing that a repulsive force permeating all of space was needed to counteract gravity in order to maintain what he then thought was a static universe. He also collaborated with Otto Stern to calculate the effect of zero-point energy on hydrogen molecules. The results matched the experimental data, but he did not connect the two. Less than 10 years later, Einstein changed his position on both issues. It is said that he called the cosmological constant his biggest mistake, but as it turns out, Einstein was right to introduce the cosmological constant, but he was wrong to dismiss the concept of zero-point energy. The idea of zero-point energy in the mid-1920s. At that time, the legendary physicist Werner Heisenberg entered the scene. In the spring of 1925, Heisenberg was deeply pondering the problem of hydrogen spectral lines, and then, in the early hours of one night, finally began to understand how the hydrogen atom behaves. He started to catch a glimpse of that magical world of quantum mechanics. There, everything is a game of probability. As he realized, it is precisely this game of probability that leads to the existence of zero-point energy. To understand how zero-point energy arises, go to the kitchen and grab a large mixing bowl, drop a marble inside, and wait for it to come to a stop. Eventually, it seems like it will settle motionless at the bottom of the bowl. But is that really the case? Can we truly pinpoint its exact position and speed? If you zoom into the microscopic world, the answer is clearly no. Particles in the air constantly collide with the marble, causing it to jiggle back and forth, all right? So what if we remove all the air from the room and cool it down to absolute zero? Will the marble eventually come to rest at the bottom of the bowl, or will it still move? The answer is, it will still move. Heisenberg realized that uncertainty always exists. The key to quantum mechanics is that it is a game of probabilities. You can only deal with possibilities. As it turns out, the more precisely you know a particle's position, the less you know about its momentum, and vice versa. This means, if we shrink a marble down to the size of a fundamental particle, we can never say it is sitting perfectly still at the bottom of the bowl, because that would mean we know both its position and momentum precisely at the same time. Heisenberg's uncertainty principle and the laws of quantum mechanics tell us that is impossible. In the microscopic world, there always has to be some fluctuation. Let us get back to that cosmic marshal. He is determined to clear all matter and energy from the universe. Before he arrives, the universe is filled with all kinds of particles. These particles are actually just ripples in the fundamental fields of nature. An electron is a ripple in the electron field. The Higgs boson is a ripple in the Higgs field, and so on. You can think of these fields as an ocean. Particles are like ripples on the surface of the sea. What the cosmic law enforcer really wants to do is to eliminate all the ripples, to calm all the excitations of these fundamental fields. He tries to make the ocean of reality perfectly flat, but he simply can't do it. Heisenberg's uncertainty principle means he will never be able to make the ocean completely still. There will always be a bit of quantum fluctuation, tiny, fleeting ripples in the fundamental fields, but these ripples do not correspond to real particles you can touch or even grab, like real electrons or photons. If they were real, they would have been taken away by them long ago. Instead, they are something more mysterious. They are virtual particles, fleeting ripples in the ocean of reality. These virtual particles are constantly appearing and disappearing out of nowhere in the vacuum. It is like a pot of boiling soup. You can't catch them. They give rise to vacuum zero-point energy. But does the energy produced by these fleeting virtual particles really exist, or is it just a theoretical construct? The answer is, it does exist, and it is incredibly powerful. We have already demonstrated it experimentally. They directly measured the force produced by vacuum energy. This is known as the Casimir force. Simply put, when two objects are extremely close together in a vacuum, the vacuum energy between them changes. This creates a measurable force that pulls them together. This force is ubiquitous in the microscopic world. It is even one of the secrets behind a gecko's ability to climb walls. Now that we have proven that vacuum energy is real, the next question is, how much of it is there? Get ready, because the theoretical calculations are going to blow your mind. Let us do the math. In a vacuum the size of a cup of coffee, just how much energy is hidden inside, according to the core principles of quantum mechanics? The Heisenberg uncertainty principle, energy and scale are inversely proportional. The smaller the scale you observe, the greater the energy you can detect. It is like looking through a microscope. The higher the magnification, the more details you see, the richer and more intense they become. Physicists use this very principle to calculate vacuum energy. They imagine space as being made up of countless tiny packets of energy. The smaller the scale we can probe, the greater the energy contained in each packet. Just how small a scale should we be probing? Let us first go back to the 1920s, to the scale physicist Pauli used in his calculations. That is about the size of an atomic nucleus. Even at this scale, the result is already astonishing. Vacuum the size of a cup of coffee contains enough energy inside to instantly evaporate all the oceans on Earth. But we should not stop there. Since Pauli did his calculations at the Hamburg Cafe, nearly a century has passed. Physics is no longer what it used to be. The technologies we have developed allow us to explore the microscopic structure of the universe more deeply. In a tunnel beneath the mountains on the Swiss-French border lies the Large Hadron Collider, or LHARC. This is CERN's most advanced particle accelerator. The machine recreates the moments just after the birth of the universe. By smashing subatomic particles together at nearly the speed of light, these collisions allow physicists to peer into the microscopic world with unprecedented resolution. They divide the universe into fragments as small as 10 to the minus 19 meters, is 10,000 times smaller than an electron, and 10,000 times smaller than the puzzle pieces Pauli imagined. When you break the universe down into pieces this small, you find that virtual particles are constantly appearing and disappearing. The intervals are as short as a billionth of a nanosecond, filling the vacuum with enormous amounts of quantum energy. According to this estimate, the energy contained in a vacuum the size of a cup of coffee would be enough to blow up an entire planet. Not just once, but over 100 million times. It could wipe out every planet in an entire galaxy. The collisions in the CERN tunnel represent the cutting edge of experimental physics today. This is limited by our technology and, of course, by funding. But there is no reason to believe that physics can't go beyond this point. With better machines, we can imagine peering even deeper into the microscopic world, probing the universe at even smaller scales. So how far should we go? We could imagine dividing the universe into fragments as small as the Planck length, which is more than 100 trillion times smaller than the scale of CERN's experiments. The Planck length is the distance at which the very fabric of space and time begins to lose its meaning, because it is overwhelmed by quantum effects. If we try to divide the universe into pieces smaller than the Planck length, the very concepts of space and time begin to break down. But even a tiny box the size of the Planck length is enough to cause concern. If we split the universe into fragments that small, we would find that a vacuum the size of a cup of coffee would contain a googol, 10 to the power of 100 gigajoules of energy. That is enough to blow up every planet and star in the observable universe over and over again, and again more than a trillion times. Of course, this is still just a cut-off point. If we could somehow go even deeper, the energy would be infinite. Should we be worried? Knowing that the vacuum, right around you, between air molecules, and even in the gaps between the atoms in your body, there is an enormous amount of hidden energy. Should we be afraid? Well, in a world without gravity, there is nothing to fear, because this zero-point energy is constant. The energy density of the vacuum is the same everywhere. That is why we sometimes call it the cosmological constant. To build a weapon capable of destroying planets and galaxies, you need a difference in energy. A gradient in energy density is required to produce force. The true ground-state vacuum energy density of our entire universe is constant throughout all of space. There is no gradient. You could not even crush a grape with it, let alone a galaxy. Without gravity, this vacuum energy can't reach you. But what if you add gravity? Well, then the story is completely different. With gravity, vacuum energy becomes wild. To understand this, we need to understand how gravity works. Einstein told us that gravity is fundamentally different from the other basic forces. In a sense, it is not really a force at all. Gravity is actually the shape of spacetime, and this shape is molded by the energy contained within spacetime. So it is not just mass that curves spacetime, because mass is just one form of energy. All forms of energy curve the spacetime around them, creating the distortions we perceive as gravity. Zero-point energy is no exception. Vacuum energy, the cosmological constant, no matter what you call it, even if it is the same everywhere, it will still curve the shape of spacetime. Of course, the more of this energy you have, the more spacetime should be curved. That is why Pauli claimed that the universe could not even reach the moon. He calculated the energy density of the vacuum and worked out how much this would curve spacetime. It was quickly discovered that spacetime would be completely curved back on itself, so much so that the observable region could not even extend to the moon. We have already seen that Pauli actually underestimated the vacuum energy. He was limited by the experimental physics of his time. Modern estimates show that there is so much energy in the vacuum of the universe that it should be crushed by its own weight, bent into nothingness. It can't even extend beyond the atoms at the tip of your nose, let alone reach the moon. But now we have to state an obvious fact. The universe does extend beyond the tip of your nose. In fact, it is 100 billion times farther than the distance to the moon. The edge of the observable universe is about 47 billion light-years away. If the cosmological constant really exists, then it is much smaller than we expected. It should be more than a googol times smaller than theoretical predictions. The energy stored in a vacuum the size of a cup of coffee would not be nearly enough to destroy a planet or a star. It is not even enough to crush the smallest insect in the world. This is the cosmological constant problem. We would better the most trusted fundamental theories of physics, when combined, predict that the universe should be dominated by zero-point energy and crushed by a cosmological constant so huge it is terrifying. Our universe should not exist at all. And yet, the weight of the vacuum is far less than we expected. This enormous contradiction. Back in the 1960s, it was formally brought to the table by a Soviet physicist. That physicist was Yakov Zeldovich. By that time, physicists already had two powerful theoretical tools at their disposal: general relativity and quantum field theory. Zeldovich was the first to combine these two theories and systematically examine the problem of vacuum energy. He used quantum field theory. He vividly depicted the vacuum as a cauldron of virtual particles, an ever-boiling soup, a ceaselessly bubbling broth. Then, he applied general relativity to calculate the gravitational effects produced by this soup. His calculations were even more precise than those of his predecessor, Pauli, and even more astonishing. Theoretically, the vacuum energy would be enough to curve the universe into nothingness the instant it was born. Zeldovich keenly realized, this is not just a calculation error, it is a profound crisis in our most fundamental understanding of the physical world. In 1967 and 1968, he made it clear by elucidating the cosmological constant, the enormous discrepancy between the observed vacuum energy and the theoretical value. This would have a fundamental, revolutionary impact on fundamental physics. From him onward, the cosmological constant problem, it officially became a dark cloud hanging over the sky of modern physics. What can we do about it? Perhaps we should take an empirical approach to the cosmological constant problem. The cosmological constant, that is, the energy of the vacuum, is simply the value we measure. If it is small, then it is just small. Who cares about Zeldovich and the predictions of quantum field theory? Who cares about Pauli and his peculiar café calculations? Maybe that is just not how nature chooses to operate. But that is not a satisfying answer. The goal of science is to reveal how the universe works, and a vast amount of empirical data points to a quantum field theory, a relativistic quantum mechanics developed after World War I, that precisely describes the microscopic world. After so many experimental successes, we can't simply abandon it. And then there is general relativity, Einstein's greatest masterpiece of genius. It describes gravity as the shape of spacetime. It precisely predicted strange phenomena, like the bending of light around the sun and the precession of Mercury's perihelion. It also has massive data support. And even today, that data is still growing. In 2015, LIGO detected gravitational waves. It added another medal to its collection. But when these two pillars of 20th century physics are combined, they predict a universe that would be overwhelmed by the immense weight of the vacuum, an unimaginably large cosmological constant. A universe instantly destroyed by zero-point energy, as Zeldovich realized more than 50 years ago. We have clearly misunderstood something, some very important things. The cosmological constant problem is a major crisis in our understanding of fundamental physics. Solving it could lead to some profound insights. A step change in our picture of how the universe really works. Another similar example is the famous black hole information paradox. Zeldovich was also involved in that. The question is, what happens to all the information you throw into a black hole? Does it disappear in violation of the laws of quantum mechanics, or does it survive? If it survives, where does it go? Just like the solution to the cosmological constant problem, the answers to these questions are expected to reveal some profound mysteries about the fundamental structure of our physical world. Therefore, theoretical physicists have been searching for a solution to the cosmological constant problem for half a century, ever since Zeldovich formulated the problem in modern terms. Many solutions have been proposed, but many have also disappeared. A common idea is to assume that the cosmological constant calculated by Zeldovich is only part of the story. That is, elementary particles contribute an overwhelmingly large vacuum energy. But there is another part, a constant from some as yet hidden microscopic world. Just happens to cancel out the part Zeldovich discovered. How and why it can cancel out with such astonishing precision is the key to this puzzle. It is like balancing the weight of a billion trillion suns with a precision down to the mass of a single electron. The most popular idea involves the multiverse, where our observable universe is just one of many possible universes. Each universe has a different overall value for the cosmological constant, and perhaps other fundamental constants differ as well in most regions of the multiverse. The scales are unbalanced. The overall cosmological constant is enormous and overwhelming, but in some rare corners of the multiverse, balance happens to work out. The overall cosmological constant is very small, just like in our universe. String theory, our most promising candidate for a theory of everything, predicts that such a multiverse might exist. It contains all the necessary hidden sectors and countless possibilities, depending on whom you ask. String theory predicts there are between 10 circumflex 500 and 10 circumflex 272s and different vacuum states, each with a different range of vacuum energy, and different universes with different cosmological constants. This multiverse is known as the string theory landscape. It is exactly what we need to address the cosmological constant problem, using an innovative, though controversial, idea in this possible multiverse. Small cosmological constants are rare. Then why do we find ourselves in a universe with an extremely small cosmological constant? At this point, some physicists advocate the anthropic principle. The idea is that universes with huge and overwhelming cosmological constants are uninhabitable because of the immense weight of the vacuum. If the cosmological constant is a large positive value, the universe would be torn apart rapidly, and matter could not clump together. Stars and planets would never even have a chance to form. If the cosmological constant is a large negative value, the universe's expansion would quickly reverse into a catastrophic big crunch, crushing everything before stars and planets could form. Only in those rare universes like ours, where the cosmological constant is unexpectedly small, are the conditions just right for a slow and gentle cosmic evolution, allowing time for stars and planets to form, and providing a home for complex life. Only in these just right circumstances, beings or species like Pauly and Zildovich exist. Only then could it possibly come into existence, and be intelligent enough to raise questions about the cosmological constant. But not everyone likes this explanation. Some people say that the multiverse and anthropic selection are unscientific because they can't be falsified, although that is not entirely true. As early as 1997, Nobel laureate Steven Weinberg and his collaborators argued that if the vacuum could account for less than 60% of the universe's total energy budget, then the anthropic principle would not be able to explain why it is so small. This is a testable prediction for the anthropic principle solution. As it turned out, less than a year later, astronomers announced the discovery of dark energy. It accounts for about 70% of the total energy in our observable universe. The anthropic principle passed its first test. But people are still searching for alternatives that do not rely on anthropic reasoning. These ideas go by many names: supersymmetry, large extra dimensions, vacuum energy sequestering, the multiverse, relativity, and so on. But so far, there is no consensus. The mystery of the cosmological constant remains unsolved. As we set out to weigh the universe, we accidentally stumbled upon one of the most embarrassing problems in fundamental physics. We have measured the mass of stars, the mass of planets, and the mass of interstellar clouds. We have measured the mass of the dark matter halo surrounding our galaxy. We have even measured the mass of the vacuum itself, and it turns out it is incredibly light. So where did all that zero-point energy go? What about that bubbling soup of virtual particles, constantly popping in and out of existence? Where did its mass go? Where did it go? It should have crushed it at the very moment the universe was born. But it did not. Our universe is incredibly light. It is a gentle giant. It allows you and me to live in a galaxy called the Milky Way, beside an ordinary yellow star, on a rocky planet. Thank you for watching. Good night.